Salamun alaikum and hello everyone. Welcome to the Advanced Theory of Computation class or Advanced Concepts in Python programming language. First, I would like to offer my condolence on the martyrdom of Mr. Khamenei, the great leader of Islamic Republic of Iran. The meeting in which we were supposed to start the Python was on February 28th, when our dear country, Iran, came under widespread and criminal attack. Nevertheless, I wish health for all Muslims in the countries of the region, and I hope God grants goodness to the dear friends in Iraq, in Yemen, in Hezbollah, who stood alongside Iran. And I would like to say that I'm very happy to see you again today. Because of this situation, our access to the international internet has been disrupted, so I have to record this video and send it to you via, I don't know, Sorush or Rubica or Bala messengers, so you can access to this video and to this class. However, let's start our class. In the first session, we talked about our approach for this course, the Advanced Theory of Computation, and mentioned that we will also become familiar with the Python programming language during this class. Python is considered one of the main programming language, and it's very important in computer science. It's very useful for engineering, for industrial application, for research. Let me once again introduce the ways you... Let me to come this slide. Yes. Let me introduce you the ways you can contact me. My university email address is z_Ghorbanali@aut.ac.ir. The Gmail, I have not access to it. And in Bala messengers, my ID is Zahra_Ghorbanali. You can send me any message you want, and I become very happy to help you and answer to your question. Python. And what's Python? Python is a very high level language. It's object oriented based, and it allows you to write programs that are clear and easy to understand, and they are easy to read, often much more readable than those written in other languages like C or CPP. The idea behind Python emphasizes on two main goals: high readability of code and high productivity. The core keywords of language are minimal. It means for, while, and something like this. These keywords are limited, and in other words, it's relatively a small language. You don't need to keep in your mind a lot of keywords, and it's good, it's very good, and it makes it very easy to learn. At the same time, Python provides a large collection of built-in libraries and ready-to-use functions that make your work more easier than other users of another languages, another programming languages. Therefore, Python can be seen as a combination of simplicity and power, which makes it an ideal language for programming and for learning. It's very good for learning. One of the most fundamental questions we can ask, let me to review it again. Well, what topics I will cover during this course? Of course, we should speak about the basic Python. It means you should know about variables, primitive data structures like hash, like dictionary, tuples, list, and something else, about the control statements, about the condition. You should become familiar with file handling concepts or handling concepts. Of course, you should learn about functions and a little about object-oriented programming. I'm not sure about design patterns and these topics. GUI, database, network and socket programming, fast API, and datasets are some more advanced topics in Python, and I'm not sure that we can cover these topics or not, but I will try. About your reference books, I really recommend you to check Python for Everyone, Python for Programmer, for basic Python. Also, there are some other books that I can show you. Let me open these files. One of them is Learn Python the Hard Way. Learn Python the Hard Way. By giving some examples and by giving some codes, and by explaining some exercises, try to learn you about different concepts in basic Python. It's recommended. And the other book is, let me to check. The other one is Python for Programmers, but I can't open it. Let me to check it. Well, it's not downloaded. That's important. But the other book is Python for Programmers that I recommend you to check. Another book is Fluent Python. It's for object-oriented programming, and it's a little more complicated than two other ones. Let me show you. I have it on my systems. All of my files are uploaded on the iCloud. So during this situation that our accession to international internet limited, I can't download them on my system. I have some of them and I have some of the other ones so Fluent Python, if you check, it's more advanced topics, and it's a little harder for a beginner Python learner, but it's a good and it's a very good book that if you want to check. I wish all of you have installed Python and IDE that you like. There are different IDE: Anaconda, Jupyter, PyCharm, Sublime Text, Visual Studio Code. These are recommended, and during this class I will use PyCharm for writing my code and showing you the examples. It's not important. Well, let's start. Well, one of the most fundamental questions that I can ask, or you can ask on me, that is, how does any computer, or my computer or your computer, run any program, including Python file or browser or Keynote application or another one? I want you to think about this question and pause this video and tell to yourself the answer. How does your computer run any program? How does a computer actually execute a piece of code? It's important. Before we start learning Python and writing programming, I want us to take one step back. We are going to give instructions to a machine, but how does this machine actually work? A computer is not an intelligent being. It does not truly understand anything, and it simply executes instructions. It's just see instructions and try to execute them. In the end, everything a computer does can be reduced to three simple steps: receiving data, what are named as input, processing them, and then, or in the final step, they produce some results which are known as output. And the brain of this system is a component that's called CPU, or Central Processing Unit. We can think of the CPU as the brain of computer, okay? It's the brain of computer, but unlike the human brain, it does not think. We as a human can think, but CPU cannot think. It simply just can't execute very simple instruction at extremely high speed. It's important. They have good speed and they can execute them very fast. Well, every program you run, it's not important things something like, for example, a game or web browser, is ultimately translated into a series of very simple instructions that CPU can understand them and can execute them. It's more important. It can execute them. So every program is translated to a simple or very simple instructions. So, what are the main components of the CPU? CPU is constructed from three main components. At first, it's arithmetic logic unit, or ALU. ALU is responsible for calculation. What does it do? It do addition, subtraction, multiplication, division, and comparison. Comparison, it means greater or less than or equal or not equal to something. Okay, so it's the work of ALU and it's the task of ALU. Another part or another component of CPU is control unit. Control unit is can act like an executive manager. It's important. Its job is to read the next instruction from the memory, tell to the appropriate component to execute it, control the order in which the instructions are executed. In other words, it determines which instruction should be executed at each moment. Okay, and the third part is register. Registers are very small and the most fast kind of memory that are located inside the CPU itself. Okay, why are they important? Do you have any idea about it? Do you know why registers are so important and are one of the most important parts of the CPU? I like you think about the answer of these questions before listening to the rest of the course. Well, the importance of registers are because the CPU cannot work directly with the data which are stored on the hard drive. Okay, and it also does not operate directly on RAM in most cases. Data must first be loaded into registers before it can be processed. Okay, so you can imagine a register as the working table of a chef. The things that chef will need to them should become onto this table, and ingredients come from the for example refrigerator can be considered as RAM, should become to table, and then processing happens. The famous CPU cycle, it's important to know about it. The famous CPU cycle is fetch, decode, execute. The CPU constantly performs a cycle known as fetch, decode, and execute, where fetch means the instruction bringing from the memory, decode, the CPU determine what the instruction means, and execute means the instruction is carried out. The cycle happens billion of times per second. Okay, so far we said that the CPU is the brain of the computer and that it simply executes instruction. No. Think. An important question arises. What instructions can the CPU actually understand? Any idea? This brings us to an important concept, instruction set architecture, or ISA. ISA, what's the meaning of the ISA, or what is instruction set architecture? It's the set of instruction that a CPU know how to execute them. Or if I want to tell it in simpler version, ISA is the official language used to communicate with the CPU. A simple example, imagine a CPU that only understands the following instructions: addition, which can be shown as ADD, subtraction, which can be considered as SUB, loading, it means loading some amount on the variables or on the registers, stores, and jump. You cannot tell it something like calculate average, because why it cannot calculate average? Because the instruction set or the official language that this CPU understands is just addition, subtraction, loading, store, and jump, and it has no idea about what is the average that you want me to calculate. I should write a small program to calculate the average by using the instruction that this CPU understand and know about it. So the calculate average instruction is not defined in this ISA, so it cannot be implemented, or it cannot be run by this CPU. Well, an ISA is not only a list of instructions. It's important to understand ISA. I tell you at first that ISA is the set of instruction that and its names show you instruction set architecture. But it's important to know that ISA is not only a list of instruction, it also defines several important aspects of how the processor works. One of the most important part are registers. How many registers exist and what and how they are called. For example, AX, BX, R1, R2. These are different naming of the registers. How it works with the memory and what's its memory model, how the processor access to the RAM. Another important part are data type. What kind of data the CPU supports? For example, it's a 32-bit range integers, it's 64-bit integers, it's floating point numbers. Example, it's important so to understand some of the most well-known ISA are x86, which worked and which are mostly and vastly used by Intel and AMD processor in most personal computers. Another one is ARM or ARM, which commonly used in mobile phones and low power devices. And another one is RISC-V, which is a newer open source architecture. For example, let's me to show you a list of x86 instructions. I bring it and take it from Wikipedia, the free encyclopedia. The x86 instruction set refers to the set of instructions that x86 compatible microprocessor supports. The instructions are usually part of an executable program, often stored as a computer file and executed on the processor. The x86 instruction set has been extended several times, introducing wider registers and data types as well as new functionality. Well, it's an example which show us some instruction, its meaning, nodes, and what's it, the opcode of this instruction. Well, the instruction, let's go through them one by one and explain this table in more detail to you. Instruction column. This column shows the name of the assembly instruction. ADD, its meaning is add. It means it would add to variable or something else. CMP, its meaning the comparison or compare operands which are going to compare their input. Notes. Let's see to the first row. Add. It's written in the notes that 1 R plus equal R slash M slash IMM. Well, what is R, what is M, and what is IMM? It means if you, I'm sorry, let me to show you, can I have any access to the, no, I cannot use any laser point or another things on this screen, I'm sorry. So I was speaking about the notes section, and I want you to look at this part. The first row, the notes column. It's written that the add instruction, which means add, how it's implemented here. R means the register, M means the memory, and IMM means immediate value. It means some constant written directly in the instruction. For example, I write A plus 10. 10 is the constant value that is written directly in my instruction. Well, this means a register can be added to another register. A register can be added to a value in the memory, or a register can be added to an immediate constant. Okay, so for example, I can write add rax, 5. This means rax is equal to what's stored on rax as a register plus 5. Okay, for compare, it's similar. It's important to check that in the compare operand, this does not really store the result. It performs a subtraction only. Check it, the second row. For comparing, it just subtract register from another register, from something that comes from memory or from immediate value. Okay, and instead of saving the results or storing the result, it's update the CPU flag. There are some CPU flag, for example 0 flag, sign flag, and other. It try to update that flags. For example, if I wrote CMP as the compare, rax, RBX, RAX, and RBX, these are 2 register. It's a subtract rax from RBX. Okay, and the result is stored on the flag. The fourth column is opcode. And opcode is the real low-level representation. This column is one of the most interesting parts. Do you know what's the meaning of opcode? Opcode means that it's the actual code that is sent to the CPU in the form of binary. Okay, CPU does not understand the ADD. It see the opcodes, and opcode is that binary representation. It's that low-level representation of the instruction. The actual code that is sent to the CPU is the opcode. These are some hexadecimal values that represent different version of the add instruction, because if you use the register or the memory or immediate value, each of them may have different instructions, so their opcode may be different from each one. Well, let's continue. We were talking about how does your computer run in program, and we talk about what CPU, what's its components. Now, suppose we have 2 processors from different manufacturer. One from Intel, one from Apple Silicon, one from Intel, one from AMD. Okay, but these 2 processors share the same ISA. What was ISA? ISA was the instruction. Let me show. ISA was the instruction set architecture. Okay, so we have 2 different processors from 2 different manufacturers, but they share the same ISA. And what was this ISA? The instruction set. Okay, my question is that, will they behave exactly the same? What's your answer? I have 2 different processors with the same ISA. Will they behave exactly the same? Yes and no. Yes, because they can run the same program, okay, and they will produce the same output. And no, because they have different speed and they have different implementation and ISA instructions. Okay, let me explain it a little better. If two CPUs both implement the same ISA, for example, one of the well-known of ISA was x80. Let's think both of them have the same ISA x80. Both of them understand instructions such as addition, subtraction, move, comparison. Okay, both can run the same executable file, and the same operating system can be installed and can run on both of them. It's important. But why? It's because the contract between the software and hardware is the ISA, and because both of them have the same ISA, they can understand the same things. As long as the processor supports the ISA, the program can run. But why I tell you no, and because of the speed and how the instructions are executed, it's because the ISA just define what instruction exists, but it does not define how these instructions are implemented inside the CPU. The implementation is more important than the existence of instruction. This brings us to the concept of microarchitecture. You can consider that I have a processor Intel Core i9 as this picture, AMD Ryzen. Both use the x86-64 ISA. So if you run a .exe file, both of them can process that and can execute that. However, one of them may execute the program faster, one of them may consume less power, one may have large cache, one may have a deeper pipeline, and something like this. You can think it about like that. Both of us, me and you, we can speak in English, and a native English can also speak English, but one of us may speak faster, one may have different accent, one may have better memory, and she or he can remind the word better than me. Okay, even so, both can understand the same sentences, but their speed is different, their knowledge is different. Okay, it's a good example of the different performance of processor with the same ISA. Well, do you remember that we said the CPU operates in a continuous cycle? That cycle was fetch, decode, execute, fetch, decode, execute, and I mentioned that this cycle will be repeated billion of times. Okay, let's go in more detail and explain it better. What was fetch? Fetch simply means beginning the next instruction, or bringing the next instruction from the memory into the CPU. The program is stored in memory. This is the green thing here is the RAM or memory. All of your program, all of your contents are stored in the hard drive some of them that are clicked and they're going to be used come to the memory or come to your RAM, random access memory. The CPU doesn't know the whole program from the beginning to the end at once, because they are stored in the different parts in the memory. This CPU simply asks, where's the next instruction? Bring it. It's what CPU needs. CPU needs to find the next instruction to be executed by it. Okay, and it doesn't know where is it, and it's just ask it. Fetch is this process, is this finding that part of code. What exactly happens during the fetch stage? To understand this, we need to introduce an important component, which is called program counter or PC. In x86 architecture, it's called also instruction pointer or RIP. But what is this, and what does it do for us here? It just stores the address of the next instruction that should be executed. Okay, so if we want to explain fetch process step by step, at the first step, the CPU look at the address stored in the program counter or PC or RIP. It's not important, the names are not important, but we call it program counter. It's easier to understand or to remember. In the second step, it reads the instruction from that address in RAM. So in the first step, CPU look at the PC call it where is the next instruction stored, then CPU reads the instruction from that address in the RAM. In the third step, the instruction is brought into an internal register called instruction register. Do you remember that I tell you the third component of the CPU is register, and it's the kind of memory that CPU works with that? Okay, in the third step, this instruction that was stored in part of the RAM is brought into internal register into the CPU, which is called instruction register. The PC is advanced to point to the next instruction. Okay, so the address that is stored in PC is changed with the address of the next instruction. After that, the CPU moves to the decode stage. If I want to give you some example, suppose the PC contains the value 100. Okay, the CPU goes to RAM, reads the contents of the address 1000, load it into the CPU, and update the program counter or PC to 1004. If we consider the instruction length as 4 bytes. Okay, if I wanted to give you some more detail, in x86 architecture, the instructions do not all have the same length. An instruction may be 1 byte, 2 bytes, 7 bytes, even up to 15 bytes. Therefore, the CPU must determine the length of the instruction so that it can correctly update a PC. So it is important what's the length of the instruction. It's not fixed in x86 architecture. This is one reason that why decoding a stage can become more complex. After bringing the instruction from the RAM into the register called instruction register into the CPU. The next step is decoding or decode. But what's the meaning of the decode? Decoding means figuring out exactly what the fetched instruction is supposed to do. The instruction is only just a sequence of 1 and 0. Okay, in the decode a step, it's figuring out what this instruction is going to do. Remember that CPU only sees a sequence of bits, a sequence of 0 and 1s. So before executing anything, the CPU must understand, is this instruction of addition or comparison or subtraction or division or what is this? Okay, and how many operands does it have? Are the operands stored on registers or are located in the memory? What's the data size? This interpretation happens in the decode stage. Okay? So, after the fetch stage, in the decode stage, the instruction is placed into the instruction register. The control unit begins interpreting the bits. The opcode is extracted. I told you what is opcode in the previous slides. The type and location of the operands are determined. Control signals are generated to prepare the CPU for execution. In other words, the decoder stage determines which parts of the CPU need to be activated. Simple example, if I want to give you for better understand this, let's think about add or addition. Suppose the opcode corresponds to an add instruction. During decode, the CPU determines this is an addition operation. The ALU must be activated. I told you that control signals in the decode steps need it determines which part of the CPU need to be activated. Okay, if I wanna to do some addition after understanding, okay, it's the addition operation. Now it's activate ALU or arithmetic logic unit. In the next step, 2 registers must be read. Why? Because in addition you need two register or 1 register, 1 memory location, 1 immediate value, okay, something like this. The result then must be written back to the destination register. It's all that it's going to do when we are in the decode stage, in the cycle of fetch, decode, and execute. The last step here is execution or execute. Execute, what's the meaning of execute? It's meaning the performing the actual operation that was determined during the decoder stage. We understand in the decoder stage what's that operation. Okay, now in the execute, I wanted to perform this operation. If decode determines the instruction is an addition, the addition is actually what's performed during execute step. Okay, if we wanted to review this process quickly, this process or this cycle contains 3 main steps: fetch, decode, execute, fetch, decode, execute. Fetch, the instruction is brought from the memory. Decode, the CPU understand what the instruction means, and execute is the operation that actually carried out. Let's look at this slide. Well, I fixed the problem with this slide and I add a little explanation on this slide that look at the above, the right side, add RAX comma RBX. It's what that add is that ISA instruction. RAX is the name of the first register and RBX is the name of the second register. The result of this operation is adding the amount of RBX to RAX and store that on the RAX. Okay. And I tell you, the CPU for performing this operation perform a cycle continuously, first decode, execute, and I told you that in the fetch process it brings the next instruction from the memory. In the decode step it determines what the instruction means, and in the third step it executes the instruction. The cycle repeats billion of time per second. Okay. However, I have a question. What does an instruction actually look like for the CPU? Does CPU see the add RAX comma RBX? I tell you here that it see a sequence of bits. Does the CPU really understand that the word add here means addition? It's my question. What's your answer? The answer is no. The real language of the CPU is not sequence. The real language of the CPU is only 0 and 1. In reality, the CPU works with the electrical signals. High voltage is 1 and low voltage is 0. Therefore, the CPU does not understand words like add or move or CMP as the compare. Okay? It only recognizes binary pattern. What is add that we write? What is this add that I write here? When I write add RAX comma RBX in the above of this page, this is a human readable representation of the instruction. But inside memory, if you go deeper and look at that, you can see a binary sequence as much like this. Add RAX comma RBX is this. And this is the machine language, which a computer that understands that and CPU reads that bits from the memory and executes them. This is the lowest level of programming, and it's called machine code or machine language. Machine code is simply a sequence of 0 and 1s. Here we need to something that become intermediate between the machine and us, and the first helper was assembly language. Assembly language is a symbolic and human readable representation of the same instructions of that bits, of that zeros and ones. So we can think it like assembly is a more human friendly representation of the sequence of instruction, and machine code is that really binary instruction which CPU understands that. But really, what is this zeros and ones in hardware? I told you zeros are representing the low voltage and ones are representing the high voltage. At the physical level, these bits correspond to transistors, logical gates, and digital circuits. Ultimately, every instruction results in electrical paths being activated or deactivated across billions of transistors inside the CPU. And it's important to know and consider. And then assembly language, we speak about it, and I told you about it to you. But question, why don't we write program directly in zeros and ones? If CPU understands zeros and ones, why we do not write our program in 0 and 1s? Is it possible? Really, in theory, it's possible. Nothing prevents someone from writing programs directly in machine code. But really, in the real world, it's unusable, and you cannot find a programmer that write code in 0 and 1s. There are multiple answers for this question, but one of the answer is that it's important your code become readable. And I told you more an important advantage of Python is that it's a readable language and it's easy to understand. Okay, if you write a program as the sequence of 0 and 1s, no one understands what is this is going to do, what's this instruction, and no one understands, is it addition, is it movement, is it a comparison, no one understands, and even is this operation on the 32-bit data or 64-bit data, which register is the destination, no one understands. The human brain understand the words better than these patterns. Even we know that the words is going to be translated to the 0 and 1s, but I as a human can't code in 0 and 1s. Another answer is that due to human error. With binary instruction, even a single incorrect bit, think the sequence must be 1, 1, 1, but you have some problem and you do some mistake and you write 1, 1, 0. It's a completely different instruction, and it can completely change the meaning of the instructions. A change in just one bit may transform the instruction into something entirely different, and such errors are extremely difficult to detect and debug them. Okay, and here assembly comes to help us and make a word a little more beautiful for us as the programmer. But we do not even write our code in assembly language, because assembly language is dependent to the computer hardware, and it's not easy for us to know the computer hardware language for every CPU and for every memory. Okay, it's not easy for us. Instead of this, we're going to use the high-level programming language, and the meaning of high-level language, programming language, is the programming language that are more close to the human language in English. and our result is that they are easier for us to understand and to remember them. We usually don't write programs directly in assembly language right there, because assembly can differ from one machine to another dependent to the processor architecture. So if I write my program in human language, like what you are looking, what's presented in this slide, it's really easy to understand. I know there's a function here. It returns a value and it's going to print something on the screen. It's not in assembly language because it's general, and it should be translated by assembly. I don't know where is assembly here. I don't see assembly, and then assembly translate this code to some sequences of 0 and 1s that my CPU understand that, okay, I need a translator that can convert this source code that you are looking at it in this picture into machine language, which the CPU can understand and execute that. This is where some things named compiler comes in. What is compiler? Let's look at this article from Wikipedia. Check the page, and I invite you to read it yourself. In computing, a compiler is a computer program that translates computer code written in one programming language, which is called the source language, into another language, the target language. Okay? So I understand. I need a translator. Okay, compiler is that computer program that can translate my source code to the target language, which is the machine code. The name compiler is primarily used for programs that translate source code from high-level programming language, for example, C, CPP, to a low-level programming language, for example, assembly language, object codes, or machine codes. For what? To create an executable program. So, a compiler takes the entire of your written program and translate it into machine language at once. But how? First, it should analyze all of your code, then convert it into an executable file, and after that after performing this translation, your program can be run. Let's look at to all of this process together. I want to explain it with an example that you can see here. It's an easy program. It contains 7 lines. At the first line, I include stdio.h. It's important to mention it's a program in C language. The second line is blank. The third line, it's int main. It means I'm defining a function in C. And the type of this function is integer. It's meaning it returns a value from the type of integer. Line 4, I define my block, my starting of my block of code of this function. In the 5th line, I'm going to print hello world on the screen. And in the 6th line, I return 0. In the 7th line, I finish the block of this function. Okay. Every part of this program, the int, the main, the parentheses, the printf, the return, all of them have some meaning for me. And it makes sense for me as a human, because it's written in high level language that is that's easy for me to understand and to check it. I know that I can see some keywords like printf, like return here. I have some string here, hello world. All of these are meaningful for me. But yes, let me show you here. When I write this program, I see just one.c here, and when I once compile it and run it, I can see that an executable file is created here in my screen and in this folder. And if I check what's the kind of this file, it's going to show me Unix executable file. It means it can be executed by my machine. What do you see here, and how you can interpret this code for me? What do you see here? I know here it's a definition of a function which is named as main. Its type is integer. In the second line, I'm defining a variable named x with a type of int, and then I'm assigning the amount of 3 to this variable x. Okay, when you look at this part of code, you understand x is a variable, 3 is the amount, is an integer, and you can follow it. But computer do not understand what is int. It doesn't understand int. What is int? It doesn't understand main. It can't see main. It see all of them as a sequence of characters that are come after each other. Well, what does the compiler actually do with this code? Let's understand the role of compiler better and explain it in more details. Compiler performs several steps to transform your human readable source code into machine executable instruction. In simple terms, it turns your meaningful code into something that CPU can understand. The first step is lexical analysis. During the lexical analysis, compiler breaks your code into a small, meaningful pieces that call token. I told you the computer see this int main as int space main parentheses and so on. Okay, lexical analysis breaks these parts and bring them together and tell, look, these are tokens and these tokens are meaningful. A token is int, a token is the name main, the token is x, it's known as an identifier. It's 30 is a number, okay? But okay, let's think all of these tokens are meaningful and there's no error here. But another question, are these tokens forming a grammatically correct sentence? I couldn't have main int, I should have int main. Okay, in Persian I can tell you سلام امیدوارم حالتون خوب باشه, but I can't tell you سلام خوب باشه حالتون امیدوارم. It's not grammatically correct, okay? So after the lexical analysis we come into the next step, which is checking if my code is grammatically correct or not, and it's known as syntax analysis or syntactic analysis or parses step. These are different names that we use here. But what does syntax means? Syntax means the grammatical rules of a language. Okay, in C programming language, you should declare the type and then name a variable and then the assignment and then amount and then semicolon. It's a grammatical rules of this language for identifying and assigning an amount to a variable. Okay, just like grammar's rules in English and Persian and Arabic. If this structure is not respected, the compiler produces a syntax error. And it's the role of parser. The parser takes the tokens in this programming language. In this step, we break the code into the tokens. In this step, parser takes these tokens and produces a theory representation of this program, which is called abstract syntax theory or AST. Something like this that you are watching on the screen. It's common that sometimes the tokens are generated correctly by the lexer, but their order might not follow the language grammar, and in this case the parser reports a syntax error. After synthetic analysis, we go to the semantic analysis. Well, there are some bombing sound here. It's not important. Well, semantic analysis. While syntax analysis ensures the code is grammatically correct, semantic analysis checks if the code is logically and semantically correct. For example, let me write something here. Int x equals to hello. Okay, in this part of code, I declare that x is form type of integer, and here I assign a string to this variable. Is it true or not? If you check it from grammatically and from the lexical analyzer or tokens, this code is true. But semantically, it's not true. An integer is not a string, okay? And it's what in the semantic analysis are going to do in this step. They check the type, they check the variable declaration, the scope, the function parameter, the operator computability. All of these are checked here and during this step. And it's important. After that, some processes like optimization and generating the intermediate code is done. After semantic analysis, the compiler moves from analysis phase to the code generation phase. At this stage, the program is translated into assembly code, and after that the linker comes into play, and the linker combines the generated object code with the other required libraries and modules to produce the final executable program. For a more compact and readable representation, machine code is often displayed in hexadecimal, not in binary form, okay? It's more compact. Well, if we have a program that has already been compiled into an executable file and can run on a computer, what happens if we give the same program to another computer? In computer 1, I write a program in C language and compiler make it the machine code of it. Can I run it on another computer or not? The answer is that it depends on several factors. One of these situations will occur. 1. If both machines, computer 1 and computer 2, if both machines have the same CPU architecture, the program runs correctly. Consider or suppose the program was compiled for x86 64-bit. The destination machine has also the same configuration, and the operating system is for both of these computers is Windows. Okay, in this case, the executable contains machine instruction that the target CPU understands, so it will run without any issue or any program or any problems. Let's consider another situation. Think the destination machine has a different CPU architecture. Okay, here in this situation, the executable is going to be run on this computer or not, if they have different CPU architecture. Think, for example, their program is compiled for Intel, a processor Intel x86, and the target machine have a processor of ARM, which is commonly used in smartphones. In this situation, the executable contains mission instruction that the target CPU simply does not understand them, okay? But what is the result? This app can't run on this CPC. or a segmentation file is going to arise. The third situation, if the CPU architecture is the same, but the operating system is different. I have two computers, one has Linux, one has Windows, but both of them have same Intel processor. What about in this situation? It again still won't run the program, but why? It's because the executable format and system call differs. The system call between Linux and Windows is different. Windows use PLR binaries. Linux use ELF binaries. Their APIs, their system calls are incompatible. So the program won't run unless you use a same hardware on both of that systems. Okay, so if you compile a C program in your computer, is it runnable in another computer or not? So I told you that it's dependent to different factors, and I figure out three situations. It's because it's the reason that when you're going to download a program for your computer, it asks you what's the type of or what's the configuration of your system. Here I'm going for example to download the Python Professional for I myself, and it tell me do you have the Apple Silicon or Intel? Okay, I have the Apple Silicon and I choose this configuration. From this above you can choose if you have Windows, you have Mac OS or Linux, and on every operating system you have choose the type of processor that you have. Let me pause it.